All right, here we go. Unit 11. Kind of like Unit 10, just a whole bunch of circle stuff. This time we're going to talk about relationships inside of circles and stuff we can talk about, such as their arcs and their chords and their secants and their tangents, a few things like that. So if you looked at the notes, hopefully you filled out the notes and you got all the definitions down. I'm just going to work through all of the examples, and I want to talk about a few theorems first. So we have two circles. So we have circle Q and we have circle T. So we name circles based off of their centers. So the center of this circle is circle Q, center of this circle is circle T. Okay, maybe these circles are congruent. All right, if we have two congruent circles, the first theorem I want to talk about is if two chords in a circle or two chords and two congruent circles are congruent. So if chord PR is congruent to chord SU, what we can say about that is the central angles are also congruent. All right, so if PR is congruent, so if chord PR is congruent to chord SU, then the central angle PQR is congruent to this central angle STU. All right, that's the first theorem. Now the second theorem, if two arcs in a circle are congruent, so if this arc right here, all right, if arc PR is congruent to arc SU, then their chords are congruent. Right? So if arc PR, not segment PR, arc PR is congruent to arc SU, then their chords are congruent. Then chord PR is congruent to chord SU. And chords are just segments, so we can notate them just like we would segments. Okay, those are the first two theorems we can talk about. We could also use a transitivity property. We could say, oh, if angle PQR is congruent to STU, well, we already know that these chords have to be, these arcs have to be congruent. So we can kind of translate that. So we can say if central angles are congruent, then the chords are congruent. The central angles are congruent, then the arcs are congruent. Therefore, if the arcs are congruent, then the chords are also congruent. All right, that's the first theorem I want to talk about. I guess the first two theorems. Now the next theorem, if we have some diameter, CD, or even some radius, I don't have a letter here, but let's call this like an R. If I have radius CR or diameter CD, whatever, if this segment here, even segment RE, okay, if this segment is perpendicular to a chord, to any chord, so chord AB, so if this segment is perpendicular to this chord, then what that does is this segment bisects chord AB. So what we can say is segment AE is congruent to segment EB. All right, that's the third theorem I want to talk about. So if RC, DC, RE, whatever you want to say, I'll say CD. If segment CD or diameter CD is perpendicular to chord AB, then let's see, at point at E, then AE is congruent, segment AE is congruent to segment EB. That's the third theorem I want to talk about. Now, the last theorem, what the last theorem says is if chords are equidistant to the centers, all right, so if VL, segment VL is congruent to segment LC, what that means is these chords are congruent. So if VL is congruent to LC, then chord YM is congruent to chord NZ. So if VL is congruent to LC, then YM is congruent to NZ. All right, and we can kind of go off of that because up here, if you look at this first theorem, since we have congruent chords, then we also get for free that arc YM is congruent to arc NZ. And then even if we wanted to, we could say that these central angles are also congruent. So there's a whole bunch of stuff we can say off of this theorem using the transitive property and substitution along with these two. We can say a whole bunch of stuff is congruent off of here. But mainly, if segment VL is congruent to LC, all right, and L is the center of our circle, then we have chord YM is congruent to chord NZ. All right, so let's take a look at a few of the examples. Now in this one, they want us to find the length of segment AB. Okay, we are given circle C. We have CP is congruent to CR. Okay, just by that last theorem we just talked about, we automatically get that AB is congruent to QS. Right, therefore, there's really not much work we have to do in this one since we know AB is congruent to QS. Right, we know QS is just 7 plus 7 is 14, so AB equals 14. Now the next one, they want us to find X. We have that this arc right here is 102 degrees. Since we have congruent chords, what that means is congruent chords give us congruent arcs. So we know this arc right here, the arc on the right, is congruent to the arc on the left. Now, we don't know what they are just yet, but we know that this one is X degrees. Since the one on the right is X degrees, the one on the left must also be X degrees. And using these three things, we can make an algebraic expression. We could say X degrees plus 102 degrees has to equal the total number of degrees in a circle. Well, the total number of degrees in a circle is 360. And that's just an algebra problem we can solve. So we have 2x plus 102 equals 360. All right, now I'll subtract that over. 2x equals 258. And then we just cut that in half. So x equals 258. That's going to be 129. 129 degrees. All right, and we can always check our work. All right, if we add 102 plus 129 plus 129, that'll give us 360 degrees. So that is correct. All right. Now, I think this was the third example in the notes. So if segment LV is perpendicular to YM, segment is perpendicular, LV is 5, let's see, LM is 13. Okay, so what they do here is they give us this distance. This is 13. What they want us to do is they want us to find this segment right here. Now, we don't even need to use any of this stuff. That's just extra information that they're giving us, okay? Everything we need has to do with this triangle right here. Notice how this is a right triangle. Okay, before we learn anything about circles, anything about trig, one of the first things that we talked about was the Pythagorean theorem. Okay, we don't know what this is, so let's just go ahead and call it x. We know the Pythagorean theorem says x squared plus 5 squared, one leg squared plus the other leg squared equals the hypotenuse squared. Okay, maybe you saw this and you realized, oh, this is a Pythagorean triple. You already know x equals 12. But if you forgot about your Pythagorean triples, you could always do this the long way. X squared plus 25 equals 169. Subtract it over. X squared equals 144. Therefore, x has to equal 12. Okay, we're not done though, because we just know that this part of the circle equals 12. That's not what they're asking for. They're asking for this entire thing. Okay, this is where we have to use the fact that it's perpendicular. Since we have a segment right here that is perpendicular to a chord, then what we know is that segment YV is congruent to segment VM. Okay, LV bisected this chord. So if we have VM is 12, then we know that YV is 12. Therefore, YM, okay, this chord right here, YM, is just 12 plus 12, or 24. All right, 2 more. Second last one says, sketch circle R with a radius of 5 times c squared 3. They also want a chord XY that is 5 units from R. Okay, so if we have our radius here, the radius is 5 times the square root of 3, and they want a chord XY 5 units from R. So let's go ahead and draw this chord. All right, so we have our radius and we have our chord. We know that this distance right here is 5 units. We also know that this distance is 5 times the square root of 3. So what we can do is, since this is the radius, what we can do is I'm going to draw another radius. I'm going to start at the center, and I'm going to connect it to the end of the chord. All right, we know that this is chord XY. Since the radius on the circle is 5 root 3, we know that this distance right here from R to Y is also 5 times the square root of 3. Okay, what I'm going to do is I'm going to draw this in a way that it is perpendicular. That way, I can use Pythagorean theorem. All right, so this is a right angle. I'm going to have a 5 right here. I'm going to have a 5 times the square root of 3 there. Just going to have to use Pythagorean theorem. So let's go ahead and call that x. We know 5 squared plus x squared equals 5 times the square root of 3 squared. So this gives us 25 plus x squared equals 5 squared is 25. The square root of 3 squared is 3. So 25 times 3 gives us 75. Therefore, x squared has to equal 50. Go ahead and square root both sides. So it gives us x equals square root of 50. But we can always simplify that down. 50 breaks down to 25 and 2. So what this gives us is square root of 25 times square root of 2. Square root of 25 is 5. So we have x equals 5 times the square root of 2. Okay, now this segment right here is just half of the chord. Okay, so what we have is this whole chord as a length of just twice this number. So basically, chord xy, all right, chord xy equals twice this number. So 5 root 2 times 2, that just gives us 10 times the square root of 2. All right, very last one. We're going to have to draw a little bit. An engineer is designing a service tunnel to accommodate 2 trucks simultaneously. If the truck can accommodate a width of 18 feet, what is the greatest truck height that the tunnel can accommodate? Okay, so it looks like this is where the road starts. All right, and I guess this is 6 feet above the bottom of the circle. We need a flat part to accommodate for the road. We can't have trucks driving on a curved surface, so we have to flatten out the bottom. So we know that this piece right here is 6 feet. Okay, we know the 2 trucks, I guess the tunnel width is 18 feet. If we want to accommodate 2 trucks in an 18-foot span, we know that each truck is at least, or it's at most, 9 feet across. So we're just taking that chord of 18 feet and we're just going to cut it in half. We know that the diameter of the circle is 27 feet. All right, so if the diameter equals 27 feet, then the radius must equal half of 27, so that's just going to be 13.5. Okay, so if this is how wide the truck is, what they want to know is what is the maximum height of the truck. Okay, we know the road is 6 feet from the bottom of the circle. So we have everything we need. We know the radius of this circle is 13.5. And it's going to be 13.5 whether you draw it here, 13.5 whether you draw it going this way. It really doesn't matter, because what we can do is we can focus in on this triangle right here. Okay, since we have a 9-foot span up here, what I'm going to do is I'm going to take that 9 feet and I'm just going to drag it down here. Okay, I'm going to do that in such a way that we have a 90-degree angle, and what we have is just another Pythagorean theorem problem. So let's go ahead and call this side of the triangle x. All right, so let's just draw our triangle over here. So we have 13.5 from the center of the circle to the corner of the truck. So 13.5, we have a 9-foot wide truck. What we want to do is we want to figure out this distance here. Okay, so that's just another application of Pythagorean theorem. So x squared plus 9 squared equals 13.5. Let's go ahead and do some quick math here. 9 squared is 81. So we have 13.5 squared minus 9 squared. What we have to do is we have to take that number and square root it. So it'll be a little bit bigger than 10. So 10.06. Okay, now we're not done. We don't want to say the height of the truck is 10 feet tall, because from the center of the circle to the top corner, right, you got to keep in mind this was x. We very easily could have done the 13.5 down here. Keep in mind that this is also x. Right, so basically, what we need is the height of our truck is just equal to 2x. So all we have to do is double this number. So the height of our truck height of the truck is just twice this number, so we're going to call it 20.12. 20.12 feet. All right, now the very last part of the directions says that we have to subtract 0.5 feet to accommodate for fluctuations in the pavement. So if we just subtract 0.5 from that, 20.12 minus 0.5, that gives us 19.62 feet. So our truck is 19.62, or the maximum height that our truck can be is 19.62